Good.
Yeah, hi, my name is Sebastian.
My name is Isfandia, as already introduced. So let's dive into it. In many applications, you have competing utility and privacy requirements, right? As we have seen. Let me give you two examples, statistical queries that we have seen. You want to have an accurate query, that's the utility requirement. You want to protect the entries of individuals. You might also have private machine learning. We have seen instances of that, where you have queries to a black box model. You want these queries to be accurate on one side, and you want to protect sensitive training data on the other side.
That's true, but I mean, come on, let's get to the point, right? Why are we listening to that? We've listened to lots of cool works on that already. In practice, we want to do privacy under continual observation, right? There's more exposure. More exposure means more leakage. So, let's just talk about that, right?
Okay, thanks. Yeah, that's an important point. Okay, what does high exposure mean? For database queries, it means a high number of database queries, right? For machine learning, it means a high number of queries to the machine learning model or a high number of training steps on sensitive data. So continual observation leads to more leakage. And what we typically do is we add noise to the computation result, and that helps a lot and leaves you a little bit of leakage, a drop of leakage after one step, and a full rainfall after many steps, right?
Yeah, that's true. I mean, the leakage becomes worse and worse, right? So what could we do? We could just vamp up the noise, right? Just make the noise kind of extreme, have much more noise. Then the leakage for an individual step becomes kind of really, really tiny, and then overall it becomes still, nice and small and all right, I guess.
Sounds like a good idea.
Yeah, doesn't it?
Well, more noise renders the results of the computation less accurate. We have seen that. That's the utility privacy requirements. And that's where our work kicks in.
That's right. I mean, prior work already has some kind of nice trade-offs. You can look at the degree of noise and how that influences the degree of privacy that you have. And what we basically do is we give better bounds. Now, what does that mean? It means that you get the same amount of privacy, right? By using less noise. So you can have more utility in your mechanism, but you get the same privacy guarantee overall.
Exactly, and we're talking about the same mechanism. It's just a tighter bound. So these tighter bounds also give you more privacy guarantees, more provable privacy for the same degree of noise. That also means more tolerance to exposure, while your privacy guarantees are very good. And that's where our work kicks in. So we give tighter bounds for approximate differential privacy under continual observation. We introduce a numerical approach, and let's talk about that.
All right, let's just use a very, very simple running example, right? Let's not make it too complicated. Let's just say, I don't know, there's a TV, and we want to know a mechanism just outputs the channel that's being watched, right? That's just the output is a TV channel, and now what you want to figure out potentially is whether Isfandia or me is watching something. So there's a probability distribution over channels for me and a different one for Isfandia, right? I think for this talk we can use that as a running example.
Come on, this is really unrealistic. The secret is now an input bit. Why don't we consider this real mechanism? Like you have a database as input, you get queries as inputs, you compute the query on the database, then you perturb it, and you have the nice Laplace distribution. But here you don't have a single pair of distributions. You have infinitely many pairs of distributions.
Right, I guess that's a valid concern, right? Here we do have infinitely many possible distributions, but I mean, if you look at the paper, we have a whole section that talks about why it suffices to just look at a single pair of distributions. And let's just look at it for this single example, right? For the Laplace mechanism, you typically don't look at all potential queries, but you just compare Laplace centered at 0 with Laplace centered at 1. And this is if your sensitivity is 1, right? And as long as the sensitivity is in that is worst case, and it's fair enough, and it's sufficient to just analyze that, right?
Okay.
So I would say let's just stick to the very simple example. Okay.
Good point. Good point. So let's talk about approximate differential privacy. How is privacy defined?
For the fourth time. I mean,
okay. Let's not do that. But we talk about approximate differential privacy. You also have a delta. That's the only thing I'll say. So let me give you a different representation of that. We actually prove in our paper that for every epsilon, we can compute a minimal delta. And we will show you with a graphic how that looks. It's asymmetric. Here we consider A versus B. If A is the probability that Sebastian watches a certain channel and B the probability that I watch a certain channel, B is the distribution and A is the distribution. Then the red area that you see here is for epsilon 0, the minimal delta. This actually also coincides with total variation from statistics. It's also used in statistical indistinguishability, but forget about that. So we get the epsilon 0 value. That's delta of epsilon 0.
Right.
And now you can increase that. You can say, what is the epsilon of the delta of epsilon 0.1? And what is the epsilon of larger values, right? So you get a full epsilon delta graph. It plateaus at the point where the probability that I watch this channel on the left is 0 and Sebastian is non-zero. That's actually a very nice channel about bread that talks.
Oh, you're talking about Banter's Brot. Yeah, I mean, it's kind of a weird thing. But I would say these epsilon delta graphs are kind of nice. Let's look at how they change under continual observation. Yeah. Okay. Now let's look at such an epsilon delta graph. This is for one single adversarial observation, right? If you have more adversarial observations, the graph is going to look worse. So you're gonna have a higher delta for every single point of epsilon. That's right. And if you increase that, it's going to get worse and worse and worse. And eventually, if you want to compute that in a very, very precise way, you would have to really compute the product distributions of all of these histograms, even for these, what was it, like 10 or 11 channels? Right. That's kind of infeasible, right? Yeah. Now we're at 11 to the 8 potential, things that we're looking at.
And it only gets worse. Actually, R-fold approximate differential privacy, that's approximate differential privacy under composition, can be considered as a differential privacy for the product distributions. That's what we implicitly use here. So because this is infeasible, there's really great work in the literature about approximations. Here's one from the moment accountants. And you see it's great, but it's not particularly tight. And this becomes worse, in particular for very small epsilons. So how tight are these approximations, and can we do better?
Well, yeah, I guess that's the main point of our work, right? So what you can see here is the previous bound is significantly above what the actual real epsilon delta graph would be if we could analyze it absolutely precisely. So what we do is, I would say, the next best thing. We give upper and lower bounds. Our upper bounds are significantly tighter than that for previous work, for pretty much everything we looked at. And we also give a lower bound, so you know how much better it potentially could be, right?
Exactly. So now we switch to the privacy loss.
Okay, let's briefly talk about the privacy loss. Now, the privacy loss is used, for example, for concentrated differential privacy, and we use the exponentiated privacy loss, if you're familiar with that, which is basically just a fancy way of saying we use the ratio between, probability of X being from A divided by probability of X being from B, right? So probability that I watch something divided by probability that Esfandia watches something. Exactly. Now we can annotate the histogram with the privacy losses for every single bar. So we get infinity for the first one. Let's just not care about the math too much. We get 0 for the second one, for the last one, that just Esfandia watches, probably some kids channel or something. And we get some values for the bars in between, right?
Yeah, Avatar: The Last Airbender. That's awesome. Okay, and let's do the math actually. The red areas that I showed you correspond to this formula that we have here. The probability that Sebastian watches a certain channel minus either epsilon that I watch a certain channel. And the sum over all atomic events.
So this is basically the formula that allows you to compute the correct delta for any given epsilon.
Exactly, thanks. The minimal delta for a given epsilon. Now we observe that this privacy loss that we have here, the exponentiated one, can be massaged around, and we get we can characterize the probability that I watch a certain channel with this privacy loss. If we plug that in, we get simple math. If we factor out A, and now we have a formula where only the exponentiated privacy loss remains, and the blue probability, the Sebastian's probability. So let's get rid of the Esfandia stuff, right?
Yeah, I think that's a great thing. Let's just remove all of Esfandia's histogram, and now we only need to keep track of the privacy losses, right, and of the probability masses in there. And we see that some of the privacy losses have the same values, right? We have the same privacy loss at different points. We can just combine them all together and still compute the same guarantee without losing anything.
Right. Then let's order them.
Okay. Cool. We ordered them. Nice.
So how does composition now work, right? Can't we also express that with the privacy losses?
Right. I think this is where it starts to become interesting. We see that the privacy loss of some output after composition is just the product of the privacy losses of the individual events without composition.
That's nice. But look, use subsequent executions and independent distributions. What's happening?
Ah, right. Yeah, all this problem with dependence and independence. Okay, let's digress a little bit, talk about that. There are three types of independence that we could have. The first one is independence of random coins of our mechanisms, or of the noise that we draw and that we add, right? I would say that almost all other works use that and require that as well. Maybe the last one that we've just seen doesn't really, and we have to take that into account a little bit. But ours definitely requires that the mechanism uses random coins for every subsequent call, right? Okay. The second one would be that subsequent queries may depend on previous answers.
That's important.
That is important, but it's also fine. We can cover that, so can most other work, as long as the sensitivity doesn't increase.
Ah, that's the worst case distribution, the 0 and the 1
exactly.
You had in the Laplace example.
That's it.
Okay.
And finally, there's this real adaptiveness where the mechanism itself might mutate depending on what it did previously, and maybe add whole different shapes of noise, or maybe even allow the adversary to choose the mechanism. Honestly, we can't do that. So can almost no other work that we've looked at, with the noteworthy exception of this privacy filters and automata paper.
Yeah, that's a great paper. Okay. Let's talk about what we actually do. So far, we didn't approximate anything yet. We should start doing that, because otherwise it remains infeasible. So let's approximate the privacy loss. Any ideas?
Well, how about we just, do what's on the slide, and we just choose some factor f, and we just, say that we have this exponentially distributed buckets. That's why there's a bucket on the slide as well. And we just put the masses into the bucket that they fit to best.
Yeah, we round the privacy loss up. Right?
That's true.
So let's make this a little bit larger. For one example, very nicely flown, this probability mass, thank you. Yeah. This probability mass goes into that bucket that is smaller than f to the I, where the privacy loss is smaller than f to the I and larger than f to the I minus 1. Then, for reconstructing the probability that I watch this channel, we actually now get an under-approximation, because we use f to the I as a privacy loss for this event, and that's not true. But that's where we make an error. However, we can quantify this, and in the paper you can read it up, how we use this quantification of the error to also get a lower bound. In the talk, we'll not talk about that.
So, just real quick, what we see is that the real privacy loss is between f to the I minus 1 and f to the I, and we over-approximate that by saying, let's just assume it's f to the I, right? Okay, cool. Now, how does composition look? Now we can see that since we only look at f to the I and f to the j here, we can just sum the exponents.
Exactly.
That's so simple. That's much easier.
Yeah, that's why we did the exponentially distributed buckets, right?
Yeah, cool.
Exactly. So how does that look with the buckets?
Okay, let's just say we have two such bucket distributions, right? The first one has f to the minus 5 to f to the 5, and the last one as well, and we have a special bucket for the infinities. Okay, let's compute a combined bucket distribution after a single step of composition. And let's just, for simplicity, just look at the f square bucket in the new distribution. How can we compute that? Well, we just look at the matching ones. We look at f to the minus 3 and f to the 5, f to the minus 2 and f to the 4, and so on. And we combine them all together. Let's just go through that. Okay, cool. And then we have computed this single bucket.
Very nice. So the problem is this still explodes. If we start with 5 buckets and do one self-composition, so the bucket composed with itself, we have 9 buckets out of a sudden. If you compose that with yourself, then you have 33 buckets, and this will explode after some time. So I suggest we just cut it off. We set a limit. We want to have an efficiently computable implementation. So we say after minus 5 and after 5 plus the infinity bucket, we cut it off and we collect all the mass of the privacy losses that are smaller than f to the -5 into the -5 bucket, and everything that's larger than f to the 6 we collect into the infinity bucket.
I mean, I can see how that works for a couple of compositions, because the outermost privacy mass is going to be really, really small. But after you do that for some time, won't this infinity bucket basically collect all the mass? Won't that explode as well?
Yeah, that's true. That's true.
I guess I have an idea.
Okay, go ahead.
So what happens if we square this factor f that we have? So we have f square now, right?
What should that help?
Well, we can now basically combine neighboring buckets together and compute out of f to the -5 and f to the -4 a new f to the -2 bucket. So it's f squared to the -2, which is kind of the same as f to the -4. And we combine that, do that again and again and again. And at the end, only have about half as many buckets as we started with, and thus, don't have this issue.
Very nice. Very nice. Let's get to some numbers. So we have an unoptimized implementation, and we had a very bad one. So David Sommer, with whom we work, they re-implemented it. Thanks to you. And now it's pretty good, but it's still there is a lot of optimizations we can still do. It's 405 lines of code, and previously it was 2,000. The computation is actually dominated by this composition operation we talked about. You could do an FFT-based convolution, which we didn't for numerical stability reasons. We now have the n-squared normal full convolution.
And let's keep in mind this n here relates to the number of buckets. Yeah. That's just dependent on how fine-grained you want the computation to be. Right? It's not dependent on how many compositions you did previously or something like that. It's just how fine-grained you want to have your composition.
Exactly. And if you now use 100,000 buckets, which is 10 times as much as we use for our graphs that you'll see in a minute, you have 13 seconds per composition operation. And that's okay, because we can do repeated squaring, right? If you want to have 2 to the 20 composition, then you just do 20 self-composition operations.
That is, as long as the mechanism doesn't change. We can deal with different mechanisms,
yes,
like a sequential composition of different mechanisms. Then, of course, it's less efficient. But if the mechanism is the same, you can always do it really, really efficiently.
Exactly.
Okay, so how tight are these bounds? Graphs.
Good. Let's look at the graphs. What we get is the following epsilon delta graph. I'm not sure whether you can read everything. Please note the lower 2 lines are ours.
Yes, the lowest stuff is ours. It's always
so the blue dotted line is the lower bound that we compute. The upper solid line, the red one, is the upper bound that we compute. And you can see they drift apart from each other at the point where our approximation breaks down. But these are only 10,000 buckets, and you saw the performance numbers for 100,000. That would be much better. And actually, the re-implementation of David is much better than these graphs. You can try it out. So we have other state-of-the-art bounds. The black one is the moments accountant bound, which is really good in many cases. The red one is the concentrated differential privacy bound, and the green one, which you probably can't see because it's so tight, is the Koff bound, the Kairos and Viswanathan bound.
Yeah, that's the composition theorem for differential privacy. Exactly. And you can see that for Laplace, it's really, really good.
Yes, but only for Laplace. Look at Gauss. Here, the Koff bound, the green one, actually is very untight. But you can see the moments accounted is still pretty good, and the CDP bound is also pretty good. I think you can improve the implementation of the CDP bound even more if you want. But our upper and lower bound for this example of 500 compositions here still is pretty good. If you look at the rightmost graph, though, that's the stochastic gradient descent of Abadi and from 2 years ago CCS. And there they actually developed the moments accountant with in that paper. And you can see this bound is not bad by theirs, but ours is orders of magnitude better.
Right. So that tells you that probably if you want to do something like stochastic gradient descent, you can use our buckets implementation to compute your privacy analysis. And this means you probably can add less noise and still get the same privacy guarantees, which hopefully leads to better convergence and better models and happier analysts.
And the rightmost is not 512 compositions, it's 60,000 compositions. In the paper, we also have one with a few million compositions. So, for time reasons, shall we skip the slide?
Yeah, I guess for time reasons, we can skip that slide. We can say for the number of compositions, like over the number of compositions, you can also compute what e to the epsilon you can reach as long as delta has to be below 10 to the minus 4. And you get graphs as well, and ours is the lowest again, which is good again. You can also look at that in the paper, ask us questions, approach us after the presentation for that if you want.
And you can look at the webpage. We made a webpage for you to play around with this stuff.
Yeah, that's true.
And we'll have a demo because the webpage was developed by David Sommer and us. And we'll present the webpage and how it works there.
Yeah, there's a poster actually, like a poster/demo at the demo session tonight.
Right. So what we did is we have a novel approximation of leakage, we compute upper and lower bounds, and we have a Git repository where everything is available publicly.
Yeah, that also allows you to just install and run the code for yourself, play around with it, find errors. Hopefully there are none, but
Yeah, please tell us.
All right, I guess. Thanks for your attention. Also, the buckets are floating because they're in space.
Any questions for the Nano Duo?
Nothing really? Come on, guys.
Thank you for the entertaining talk. So your result didn't show the first kind of it's called advanced composition, just the K-way composition. I mean, so how bad is that compared with? It's just too bad out of the.
In epsilon, in delta?
It's kind of you compose the K epsilon dp, you get the epsilon delta with the kind of square root.
Exactly.
Yeah.
This was a great paper, right? So let's not forget about that. It had the square root factor, so asymptotically it has had an improvement. But we're in the paper, we actually have a comparison against that. And for the delta value, we have 7 magnitudes better after millions of compositions. That was we used as case study the anonymous communication network analysis. You can have a look at the paper. We have a comparison there. It's just not the state-of-the-art bounds. That's why we didn't include them.
Yeah, that's true. We analyzed the privacy analysis of Vuvuzela that uses this advanced composition theorem as a bound.
Okay.
But yeah, the one by Karasu and Viswanath is better, but ours is better still for everything except Laplace, where we are only just slightly better.
All right, I think we'll close it from there. Do not disconnect. Let's take a moment to thank all of the speakers in this session.